Hey class, today we're going to continue on with learning about our gas laws and talk about something called the combined and ideal gas equation. So this is just a recap, so it's not really in your notes. All three gas laws covered in the last section, which was Boyle's, Charles, and Avogadro's, were obtained by holding at least two of the four variables constant. Again, those four variables are pressure, volume, temperature, and then number of moles. Now, when we held two of them constant, we wanted to see how did they affect the remaining ones. So for example, in Boyle's law, we looked at volume and pressure. At Charles' law, we looked at volume and temperature. And then in Avogadro's, we looked at volume and number of moles. If you ever see this little figure here, all it means is proportional to. So what we see now is we're going to learn about something called the combined gas law. We often face situations in which three variables, such as pressure, volume, and temperature, all change, but the number of moles remains constant. In this type of situation, we would actually use something called the combined gas law. The reason it gets its name is it actually combines two laws together in order to create it. And one of those laws that it uses is Charles' law. Because of this, whenever we see this combined gas law, we must still remember that the temperature must be in kelvins. Here we get P1 times V1, such as Boyle's law, and then we divide it by T1 like we do in Charles, equals P2 V2 divided by T2. Here again, 1 is going to mean before the change, and then 2 typically means after the change. So we're going to look at an example. It says, if I initially have a gas at a pressure of 12 atms, a volume of 23 liters, and a temperature of 200 Kelvin, and then I raise the pressure to 14 atm and increase the temperature to 300 Kelvin, what is my new volume? Just like any of those previous problems, I always tell people to list the variables. P1, V1, T1, P2, V2, T2. Right off the bat, I see words that indicate what did I start at, and that word is initially. So initially means that's where I began. So 12 atm would be my pressure, my volume would be 23, and my Kelvin is 200. Then I'm going to see, well, what happens after? Well, if I raise the pressure, that's a change, so my new pressure is going to be 14, my new temperature is going to be 300, and then V2 is going to be X. Now, before you continue, always check that your temperature is in Kelvin. Because my temperature is already in Kelvin, I do not need to change it, but if you did, don't forget that Kelvin equals degrees Celsius plus 273.15. So if these were in Celsius, you would have to add 273.15 in order to get them into Kelvin. From here, we can actually plug in what I know. 12 times 23, so again, P1 times V1. We're going to divide that by my T1, which was 200. This is going to equal my P2 times my V2 divided by my T1. If you ever have a problem set up like this, I still like to use the butterfly method and cross multiply and divide. So here, if I cross multiply, I end up getting 12 times 23 times 300 equals 200 times 14 times X. Then I can multiply this across and I get 82,800 equals 2,800 X. We're going to divide by the number attached to X, and we end up getting X equals about 29.5714 with a bunch of other numbers. However, just like anything in chemistry, we're going to round to the correct number of sig figs. My lowest number of sig figs is 3 based on this 12, 23, and 14. So we're going to make sure we rounded 3 sig figs here. 29 point, that rounds that up to a 6. Just like problems on the previous lesson, my pressure units are always going to match. My volume units are going to match. And then again, my temperature units are going to match. So because I'm looking for volume, I'm going to look at my original volume measurement. And that original volume was 23 liters, which means that this must be 29.6 liters as well. The other thing that we're going to look at is something called the ideal gas law. When we actually combine all of the laws, we get that volume is proportional to moles times temperature divided by P. And so that doesn't really mean a lot, but what we do need to understand is it results in an equation called P times V equals N times R times T. A couple things to note about this equation is P stands for pressure, V stands for our volume, N is our moles, R, we're going to actually learn that that's a constant coming up on a different slide, and then T is our temp. So how do we get this? This ideal gas is a hypothetical gas whose pressure, volume, and temperature relationships are described completely using this kind of equation. And in order for this equation to work, we make two big assumptions. The first assumption that we make is that molecules of an ideal gas do not interact with each other. The second assumption that we make is the combined volume of the molecules is much smaller than the volume of the gas occupies. In other words, we consider that molecules take up no space in the container. So let's break down again that equation like I did on the previous slide. So this part should be in your notes. R is the one thing that I said we would talk about. R is something known as the gas constant. Values of R can change depending on what units you use for pressure, volume, moles, and temperature. And so in our case, we are going to use the value of R equals 0.08206. Now we are only able to use this as long as we make sure that each of our variables are in their specific units. Because of this, temperature should always be in Kelvin. Your amount of gas should be in moles. So that means if it's in grams, we must change it to moles, again, using molar mass. Our pressure should be in ATMs. So that means if it's in torr or pascals, we must do what we've done in the first lesson and convert that. And then our volume must be in liters. Other units can be used, but then it's going to change your R constant, and I do not provide you other R constants. Other R values would be things like if you were to use meters cubed or pascals or torr or liters. I don't provide you with these. I always provide you with this value here. So again, you want to make sure that you're working with the correct units. The last thing I want to talk about with ideal gas law is there's something called standard temperature and pressure. So that's what STP stands for. If you ever see a problem that says you have a gas at STP, you are always going to plug in the following numbers in for those variables. For the temperature, you're always going to plug in 273.15. And for the pressure, you're always going to plug in 1 atm. Basically, this says the volume occupied by 1 mole of an ideal gas at STP is about 22.41 liters. This is known as the molar volume of an ideal gas at STP. This also ties into Avogadro's idea that if you had 22.41 liters of a gas at this temperature and this volume at this pressure, we are always going to see it have the same number of molecules. So here we have an example problem. It says, at what temperature will 0.654 moles of neon occupy 12.3 liters at 1.95 atmospheres? Again, the R constant is 0.08206. So here our equation is PV equals nRT. And this equation is really important. We're going to be using it here on out. So familiarizing yourself with this is actually going to become very crucial. We're going to list out our variables, PV, nRT. We already know our R value, so I'm going to actually plug in 0.08206. From here, we're just going to read our problem to make sure, one, we have our correct variables, and two, they're in the correct units. So here it says we have 0.654 moles, so that's going to go in for N. Because it's already in moles, we do not have to convert it, so it is good. Here it says we have 12.3 liters, which is actually a volume. Because this is already in liters, we do not have to convert it either. And last but not least, 1.95 ATMs. Again, since this is already in atmospheres, we do not need to convert it. So everything's in its correct units, and the only thing that we don't have is our temperature. So now we can go ahead and plug into our equation. Our pressure again was 1.95. Our volume was 12.3. Our moles was 0.654. Our R constant, and then our X. Here we're going to multiply these two values. We get 23.985. We're going to multiply the right side and we get 0.053666724x. Just like in algebra, we always divide by the number attached to x. And so when we do that, we end up getting x equals 446.92069. Now we want to have the correct number of sig figs. So since our lowest value is 3 for both of these, we're going to round to 447. Because this requires specific units, we should recognize that temperature should always be in Kelvin. So this is 447 Kelvin as our final answer. And that's the end of today's lesson. If you have any questions, please let me know, and I hope you guys have a great day.